Welcome back to Nick's Algebraics. Today I'm going to talk about how to solve systems of equations in three variables. So the first thing I wanted to mention is what a linear equation in three variables is. This is an equation in the form of ax plus by plus cz equals d. And this is where a, b, and c all cannot equal 0. Because if one of them is 0, let's say the c equals 0, then this cz term here would cancel out. And it wouldn't be a linear equation in three variables because it would only have two variables without the z. So that is why a, b, and c are not 0. So this ax plus by plus cz equals d, that's an example of a singular linear equation in three variables. But once you have multiple linear equation in three variables, that is called a system of three linear equations. So this is equation 1, this is equation 2, and this is equation 3. The solution to a system like this would be an x, y, and z value that satisfy all three of these equations. So that solution is called an ordered triple. It's a set of coordinates written in the form of x, y, z, and that's the solution to a system of three linear equations. And we've seen this before with an ordered pair. It's pretty similar. An ordered pair is a set of coordinates written in the form of x, y. Let's take a look at this graphically. In this graph right here, we have two lines that intersect at a point, and they intersect at the point -1, 3. This ordered pair right here would be the solution to this system of linear equations. In this case, we have only two variables, and we've seen this before in Algebra 1. So when you have two lines with different slopes, they're going to intersect at a point, and that's going to be the solution to this system of linear equations. But this is only with two variables, but now we're dealing with a third variable, z. So you might wonder, what would a graph like that look like? So the graph of a linear equation in three variables is actually a plane. Although we're going to be working with three equations in three variables, let's just see an example of two equations where we have two planes. In this figure right here, we have plane A and plane B intersecting at line R. So when we have these two planes that are not parallel, then they're going to intersect at a line. So they intersect at an infinite number of points. The only way this would not happen is if the planes are parallel and they don't intersect at all, or they're the exact same plane and they intersect at every single point. So now let's look at the examples we're going to look at. This is only with two equations with three variables that forms two planes, but we're going to deal with three equations in three variables. So that's going to form three planes. So far we've seen that two lines with different slopes intersect at a point. Two planes that are not parallel are going to intersect at a line. So if we introduce another plane into this, then we can have an intersection at one point. So that would look something like this, where we have our three planes. That's our three equations with three variables, and they're all intersecting at one point. That's our ordered triple solution. Right here, with our two lines, we had an ordered pair solution. But this is not the only case, because you could also have infinite solutions. This is where the three planes intersect at a line in this figure shown. So this line contains an infinite number of points, so there would be infinite solutions in this case. And in this figure right here, these three planes are actually identical to each other, so every single point on these three planes would be a solution. So those are two examples where you would have infinitely many solutions. And there's also the possibility where you have no solution. This is where all three planes have no common points. Like in this example right here, the three planes are parallel and they don't intersect at all. And in this example right here, we have two planes intersecting at a line right here, but there's no point where all three planes touch. And same thing with this one. We have these two planes touching, and these two planes touching, and these two planes intersecting, but there's not a point where all three planes intersect. So let's look at an example of this. Solve the system of equations. We have this system of equations in three variables. We have three equations and three variables. And we need to figure out the ordered triple solution. We want the x, y, and z value. And the process to find this is going to be very similar to what we used when we were solving systems of equations in two variables, when we had two equations and two variables. We're going to use methods like elimination and substitution again. What I need to do is I need to get these three equations and three variables and turn it into two equations and two variables and go from there. So to get from three variables to two variables, I need to eliminate one of the variables. So looking at this, I see that we have a 2x and a negative 2x right here. So what we can do is add these two equations together, and the x's will cancel out. So 2x plus negative 2x, that cancels out right here. And we have y plus negative 3y, so that's negative 2y. And negative 8z plus 2z, that's negative 6z. And negative 7 plus 7 is 0. So now we have this new equation with just y and z. So now let's repeat this process again and get another equation with just y and z. We need to get rid of x again with another two equations to get another equation with y and z. So what I can do is I can double the first equation like that. So I would get 2x minus 4y plus 4z equals 20. I just multiplied everything by 2. And what I can do is I will rewrite the second equation below that and cancel out the x's. To cancel out the x's, I'm going to have to subtract, because the x's both have a coefficient of 2, and if you subtract 2 and 2, you get 0. So this right here, 2x minus 2x, that cancels out. Now we have negative 4y minus y. So that's negative 5y. And after that, when you look at the z terms, we have 4z minus negative 8z. So when you have a double negative, that becomes a positive. So it's basically 4z plus 8z, which is 12z. And the last part is 20 minus negative 7. So that's basically 20 plus 7, which is going to equal 27. So great, now we have two equations right here with the variables y and z. So now we can solve this using Algebra 1. Here are our two new equations with just y and z. So now let's cancel one more variable so we can just solve for the last variable. So let's see what we can cancel. We're not going to cancel out the y's because finding a common multiple with 2 and 5 is going to take a while, but we can easily find a common multiple with the z terms, with the 6 and the 12. What I can do is double the 6 and make it 12, so we can just add them together and they'll cancel out. So I'm going to get this entire equation and multiply it by 2. So it's going to become negative 4y minus 12z equals 0. And this equation stays the same. Negative 5y plus 12z equals 27. Since we have this negative 12z and this positive 12z, we're going to add them together so they cancel out, and we're just left with y. So negative 4y plus negative 5y, that's negative 9y, and negative 12z plus 12z is 0, so that cancels out. And 0 plus 27 is just 27. So we're left with negative 9y equals 27, and if you divide both sides by negative 9, you'll get that y equals negative 3. So we found the y value, now we need to find the x and the z value. So let's plug it into one of these equations with just y and z in it. So it looks like I'll pick this one right here. For y, I'm going to substitute negative 3 now. So negative 2 times negative 3 minus 6z equals 0. So negative 2 times negative 3 is 6. So this becomes 6 minus 6z equals 0. And we could add 6z to both sides and divide by 6, and you'll get that z equals 1. So now we have a y and z value. Let's find the x value. To do that, I can plug y and z to any of these three equations. And I'll choose the first one to plug it in. So we have x minus 2y, so y is negative 3. So I'll substitute that. And we're adding 2z, and z is 1. Now let's solve for x. So negative 2 times negative 3 is positive 6. So this is x plus 6. Plus 2 times 1, so plus 2 equals 10. And that simplifies to x plus 8 equals 10. So x equals 2. So the ordered triple solution to this system of equations in three variables is 2, negative 3, 1. And we figured that out using elimination, just like how we did with the system of equations in two variables. We got rid of one variable, and then we used elimination again and got rid of another variable, and we started substituting the values that we got. Just to make sure, I'm going to check my answer and plug everything into all three equations to see if I did this right. For x, we got 2. For y, we got negative 3. And for z, we got 1. So 2 minus 2 times negative 3, so that's 2 plus 6 right here. So that's 8. And plus 2 times 1, so that's plus 2, and that equals 10. So it works for the first equation. Let's plug it into the second. So we're substituting 2 for x, negative 3 for y, and 1 for z. So we have 2 times 2 is 4, minus 3 is 1, and minus 8 is negative 7. 1 minus 8 is negative 7. So it works for the second equation. So now let's do it for the last one. So 2 for x, negative 3 for y, and 1 for z. So negative 2 times 2 is negative 4. And we're adding negative 3 times negative 3, so that's positive 9. And we add 2. So negative 4 plus 9 is 5, and when you add 2, you get 7. So it works for all three equations. So that means we know that our ordered triple solution is correct. Each of these three equations here are a plane, and they're all intersecting at this point, 2, negative 3, 1. So this is an example where you would have one solution. Let's do another example. An amphitheater charges $75 for each seat in Section A, $55 for each seat in Section B, and $30 for each lawn seat. There are 3 times as many seats in Section B as in Section A. The revenue from selling all 23,000 seats is $870,000. How many seats are in each section of the amphitheater? So As you can see in this image right here, this is the amphitheater. And there are these different sections, section A, section B, and the lawn. Those are the places where people sit and where they can observe the stage right here. So let's start labeling some stuff before we get started on the problem. So I'm going to call the number of seats in section A X, and the number of seats in section B are going to be Y, and the lawn seats, we're going to label that as Z. So let's look at the first sentence of the problem. So the amphitheater charges $75 for each seat in section A. So the number of seats in section A, that's X. So we're going to start off with 75X, and they charge $55 for each seat in section B. So the number of seats in section B is Y. So that's plus 55Y, because each seat is $55. And the last part of the sentence is, and $30 for each lawn seat. So that's plus 30Z, because the lawn seats are Z and each one's $30. So it looks like the farther you get from the stage, the cheaper it is. And if you look below, it says the revenue from selling all seats is $870,000. So that's like the total income they made. So when you add the cost of all the seats together, you're going to get $870,000. And we also know that there are 23,000 seats because they sold all 23,000 seats. So when you add the seats in section A, which is X, plus the seats in section B, which is Y, plus the lawn seats, which is Z, that all adds to a total of 23,000 seats. So the difference with these two equations are, the first one is about the cost of the seats. That's why it's $75 for section A and $55 for section B and $30 for the lawn seats. And that all leads to a total income of $870,000. But when you're looking at the number of seats, you're just adding up all the seats in each part of the amphitheater, and that just equals 23,000 seats. So the last equation comes from this sentence right here. There are 3 times as many seats in section B as in section A. So section B has triple the number of seats as in section A. As you can see in the image right here, section B is about triple the size of section A. So if section A has 1,000 seats, section B is going to have 3,000 seats. So if you triple the seats in section A, you get the number of seats in section B, which is Y. So the third equation is just Y equals 3x. There's no lawn seats involved in that part of the problem. So now we need to figure out how many seats are in each section of the amphitheater. So we need to figure out X, Y, and Z. How many seats are in section A, how many seats are in section B, and how many lawn seats are there. We have one equation in here that has only 2 variables. It doesn't have the variable Z in there. So what we need to do is, with these 2 equations right here, we need to cancel out Z. So we'll be left with 2 equations with 2 variables, and we can solve from there. So I want to get rid of Z. What I can do is multiply this second equation by 30. This will become 30x plus 30y plus 30z equals 23,000 times 30, which is 690,000. And then we'll just rewrite the first equation. 75x plus 55y plus 30z equals 870,000. So now that the z terms here have the same coefficient, 30, we can subtract them. So 75x minus 30x, that's 45x. And 55y minus 30y, that is 25y. And 30z minus 30z just cancels out. And 870,000 minus 690,000 equals 180,000. So this is really good. Now we have two equations here and here with just y and x in them. So what I can do is, since this equation has y on its own, I can substitute 3x for y in this equation right here that we just made. So I can rewrite it like this: 45x plus 25 instead of y. Now I'm going to substitute y with 3x. So 25 times 3x equals 180,000. So now we can just solve for x. So 45x plus 25 times 3x, which is 75x, equals 180,000. And 45x plus 75x is 120x. And when you divide both sides by 120, you'll get that x equals 1,500. So that means there are 1,500 seats in section A because I labeled the number of seats in section A as x. So now that we have the x value, I can go back to this y equals 3x equation and substitute 1,500 for x and solve for y. So now we know that x is 1,500, so y equals 3 times 1,500. And 3 times 1,500 is 4,500. So we know that there are 4,500 seats in section B, which I labeled as y earlier. So now that we have x and y, I can pick any of these two equations right here that have x, y, and z in them, and just substitute the x and y and solve for z. So I'm going to choose this second equation here since it looks easier. So here's the second equation. So I'm going to substitute 1,500 for x, 4,500 for y, and we will solve for z. So 1,500 plus 4,500 is 6,000. And when you subtract 6,000 on both sides, you will get that z equals 17,000. Our ordered triple solution is 1,500, 4,500, 17,000. There are 1,500 seats in section A, 4,500 seats in section B, and 17,000 lawn seats. And that makes sense because if you look back at our image right here, there are more seats in section B than there are in section A. So there was 1,500 in section A because it's pretty small, and there's 4,500 in section B because it's bigger than section A, and there's 17,000 lawn seats because that's a really huge section of this amphitheater. So our solution makes sense, and you can substitute the x, y, and z values into these three equations right here to check your solution, and you'll get that it works. If you were to look at this graphically, these three equations right here represent three planes, and these three planes are going to intersect at this point right here, 1,500, 4,500, 17,000. Let's do another problem. Solve the system of equations. So again, we have these three equations, and instead of x, y, and z, they put a, b, and c, but it's the same idea. To find the values of a, b, and c, we need to cancel out one of the variables first. What I notice with the first two equations are there's a -6 and a -2. So what I can do is multiply this second equation all by 3, so the -2 can become a -6, and we can cancel them out. I'll rewrite the first equation, -6a plus 9b minus 12c equals 21. And so 3 times the second equation is going to equal -6a plus 9b minus 12c, which also equals 21. Since we have -6a and -6a, we can subtract them and they will cancel out. So -6a minus negative 6a is the same thing as negative 6a plus 6a, which is 0. So that cancels out. And 9b minus 9b is also 0, so that cancels out. And negative 12c minus negative 12c equals negative 12c plus 12c, and that also equals 0. So on the left side of this equation, we have 0. And on the right side of the equation, we're left with 21 minus 21, which also cancels out. So on the right side of the equation, we have 0. So we're left with 0 equals 0, which is always true. So this means that the first two equations that we've been looking at so far represent the same plane. The second equation, if you triple it, you get the first equation. So these planes are identical. They're the same plane. So every single point on these two planes would satisfy the two equations. But that doesn't mean there's infinite solutions yet, because we want a point or more that satisfies all three equations. So let's look at the third equation. I see that we have a negative 2a here and a 10a here. So what I can do to the second equation is multiply everything by 5, and the a's should match up. I'm not going to use the first equation and the third equation because the multiples will be more difficult to match up. So I'm going to use the second and third equation. So when I multiply this second equation by 5, I get negative 10a plus 15b minus 20c, which equals 35. And I'll rewrite the third equation under that, which is 10a minus 15b plus 20c, which equals negative 30. So since I have this negative 10a and this positive 10a, I can add them together and they'll cancel out. So I'm going to add these two equations together. So negative 10a plus 10a, that cancels out, that's 0. 15b plus negative 15b, that's also 0. Negative 20c plus 20c, that's also 0. So on the left side of the equation, I have 0, and that equals 35 plus negative 30. So we have 35 minus 30, which is 5. And that is false. 0 never equals 5. So that means this system of equations have no solution. We know that because if you think about this graphically, we have these two planes that are identical to each other. That's why we got 0 equals 0 right here. So every point on those two planes would be a solution. But we have this third plane and we got 0 equals 5. So that means that it never touches the other two planes that are identical to each other. We have two planes that are identical to each other, and we have this third plane that's parallel to those two. So there's no point where all three planes intersect, so we have no solution. Let's look at the next problem. In this problem, we have yet another three-variable system. And one thing I notice immediately is that in the first equation right here, I see that there's a 4, we have negative 6, 4, and 12. And all of those have a common factor of 2. They're all even, so what I can do is I can divide both sides by 2, just to simplify the equation a little bit. So when I divide this first equation by 2, on the left side, what I'm going to do is I'm going to divide each term by 2. So 4x divided by 2, that's 2x. And negative 6y divided by 2, that's negative 3y. And 4z divided by 2 is 2z. And that equals 12 over 2, which is 6. Okay, so now that I have the 2 divided out, I notice that in the second equation right here, I see that we have a 6, -9, 6, and 18. And all of those have a common factor of 3. So I'm going to divide both sides of the second equation by 3. I'm going to divide each term on the left side of the equation by 3. So 6x over 3 is 2x. Negative 9y over 3 is negative 3y. And 6z over 3 is 2z. And 18 over 3 is 6. So now I noticed something very interesting, that after dividing the first equation by 2 and the second equation by 3, I noticed that they're the same equation. So that means graphically, these two planes are the same plane. They're going to be right on top of each other. So I need to know what this third equation, this third plane is with relation to those two identical planes here. So what I did is I wrote the third equation under this equation right here. Notice that in the third equation, I have 5, -8, 10, and 20. And the largest common factor of those numbers are 1. So I'm not going to divide anything on both sides. So what I need to do now is I need to eliminate one of these variables. So what I can do is I notice that the coefficient for z in this equation right here is 2, and the coefficient for z in this equation right here is 10. So what I can do is multiply both sides of this equation by 5. So this would become 10z, and I can subtract both equations, and the 10z terms will cancel out, and the z term would be eliminated. So 5 times 2x, that is 10x. And 5 times negative 3y is negative 15y. And 5 times 2z is 10z. And 5 times 6 is 30. And I'm going to rewrite this equation right under this one. So now what I'm going to do is, since I have 10z and 10z, I'm going to subtract these two equations. So 10x minus 5x, that is 5x. Negative 15y minus negative 8y, that's negative 15y plus 8y, which is negative 7y. And just like I wanted, 10z minus 10z is 0, and 30 minus 20 is 10. So I'm left with 5x minus 7y equals 10. And that's very interesting because that means that these identical planes right here intersect this third plane right here at a line, and this is the line that they intersect at. So that means that there are an infinite number of solutions. The reason why we have an infinite number of solutions is because there are infinitely many points on the line. So that means there are infinitely many solutions. But be careful, because infinitely many solutions doesn't mean that every single point is going to satisfy these three equations right here. I can't just plug in 0, 0, 0 into the first equation and get 12. So 0, 0, 0 does not satisfy this three variable system here. Also, what some people would do is they would get this equation and subtract it by this equation, and they would get 0 equals 0, and that would be some sort of indication that there are an infinite number of solutions. But one thing to notice is that when you're solving a system of more than two equations, if you get something like 0 equals 5, then that will always yield no solution. But if you have 0 equals 0, like in this last problem here, that means that there may or may not be infinite number of solutions. So you have to take into account that third equation there, because notice how these two equations were the same plane, and you got 0 equals 0, and some people would stop and say infinitely many solutions, but it turns out that this third plane is parallel to these two, which means that there are no common points where these three planes intersect, and you would really have no solution. So just keep that in mind. Thank you for watching. I'll post a worksheet with the answer key in the description, and have a mathlicious day.